Everybody for the last talk of the afternoon with Rajen Shah. So Rajen is from here, so some achievements from 2017 are that he got a research prize from the RSS and that he became a father. And he will talk about the XYZ algorithms for interaction search.
Okay. Thank you very much, Marluz, for the introduction, and thanks to the organisers as well. It's been a really great conference, and it's always great to be in Cambridge. Yes, I'll talk about the XYZ algorithm. We've already heard about the ABC algorithm from so it's only appropriate, I think, that this comes at the end. So this is an algorithm that I'll try to convince you is useful for finding interactions in high-dimensional data in a computationally efficient way. And this is joint work with Jan Tanai, who's a PhD student at ETH Zurich, and Nikolai Meinshausen. Okay, so let's just set up the problem. So let's suppose we want to do regression, and we're in a high-dimensional situation. We've got p variables, and p is large. And we don't want to just look for main effects. We think that there might be some interactions there as well. Now, of course, when p is very large, even looking just for pairwise interactions can be a computationally intensive task, because we have order p squared pairwise interactions to somehow search through. So in order to make progress, what's typically done is to somehow restrict the search space. We might not have the computational power to really go and search across all of these interactions. We want to somehow prune the search space and hopefully find the important ones that way. And one common approach for doing this is to first find important main effects and then just consider interactions among those main effects that have been found by the first pass. So this is sometimes known as a screen and clean type approach, but there's lots of different variants. So one example could be that we run the lasso on our data just on the main effects, get out a selected set, then add the interactions between the selected variables to our design matrix, or augment our design matrix, and then go again with the lasso one more time, and hopefully we manage to pick up some important interactions that way. And regression trees also work in this sort of fashion, where they first find important main effects and then just consider interactions between those main effects. So they'll first find the variable that gives the best split, and then as you go down the tree, all other nodes in the tree correspond to interactions involving that first main effect. So they always require lower order interactions to be informative in order for them to consider a higher order interaction. So an issue is that this can sometimes miss important interactions. So this is just a sort of a toy example here, where we've just got a binary response in -1, 1, and the design matrix is also binary. And let's suppose that this design matrix X has IID entries, and they're taking -1, 1 with equal probability, with probability a half. And the model is an extremely simple model. We've got no noise. The response is just the pointwise product between the first two columns of this X matrix. So there's really a very strong interaction here, where we, if we were able to find it, and no noise at all. Now, if we think about the conditional distribution of the response given the first variable, well, the probability that that's one conditional on the first variable being 1, when does that happen? Well, the second variable must also be 1. And so it's this probability here, which is just a half, which is the same as the probability that y was equal to 1 anyway. So what this tells us is that the response is independent of the first variable. It's obviously, by symmetry, independent of the second variable, and independent of all other variables as well, because they were not anything to do with the response. So what this means is, if by just looking at the main effects, we're not going to find this interaction, right? There's nothing in the main effects, just looking at the main effects, that would suggest to us that this interaction is somehow present in the data. Okay. So you might sort of, this is of course a toy example, and you might say, well, this is a bit of a strange model to have, because we've got some interactions here with no corresponding main effects present, and you might think that that's a little bit strange. But then, of course, what we could do is add 1 to each entry of x, and then we could write our model in this fashion here. And so here we do have these main effects present when we write down the model, but this in no way changes the difficulty of the problem, right? We still have that y is going to be independent of every single variable, right? So although we can see the main effects in here, then they're not going to be easy to find at all, because we still have this independence. Okay. So this is a bit of a problem, because we've got this really strong interaction that we'd like to be able to find, but just using these sorts of approaches that look at main effects, we're not going to be able to pick it up. So what we can do to try and alleviate this sort of issue is, rather than in this screen and clean type approach, rather than just doing things once, just finding main effects in one pass and then adding interactions corresponding to them, we could do this sort of thing iteratively, and that sort of helps mitigate these sorts of issues. We could introduce some additional randomization, so this is what the random forest approach does, and this can help with this sort of problem. But really, this particular problem is not going to be eliminated. So this toy example which I showed here, this is actually a very difficult situation, and additional randomization or sort of iterative approaches are not really going to help there. So there's also some very nice work by Ying Fan and Jinji and co-authors, looking at transformations of the response and transformations of the design matrix, and then you can sometimes pick up interactions that way. And this can be very effective, though its effectiveness will depend a bit on the distributions of the response and the design matrix. So in the case when x is binary, as we saw here, this is not going to work so well. Okay, so this is kind of the problem that we'd like to be able to solve. And I'm going to start with we've got this sort of toy example, and I'm going to start with a sort of a toy version of the problem. So really we want to build up to be able to perform a regression where we're able to include interactions which are strong without requiring the corresponding main effects to be somehow informative. But let's start with a very simple problem, perhaps the simplest problem that we could ask in terms of interaction search, where we've just got still a binary X matrix, a binary response, and we're now looking for a pair of columns in our X matrix such that when we take the pointwise product and take the dot product of that new vector with our response, this dot product is large. Okay, so and of course we'd also be interested in this dot product being large but negative, but we can just think about replacing our response with minus y, and we'll get those interactions as well. Okay, so we'll start with this problem, and then we're going to build up to the regression problem eventually. So the first thing that we're going to do to sort of slightly transform this problem, so I've got my x and I've got my y. What I'm going to do is now multiply the ith row of my X matrix with yi, and that gives me a new matrix which I'm going to call Z. Okay, so we've got our if I look at the dot product between y and this pointwise product between columns, that's going to be the same as now the corresponding column of this new matrix Z dotted with the column of X. Okay, so now I've sort of translated this problem to, I've got a matrix X, a matrix Z, and I just want to now find columns which have large dot products. Now, if we've got two columns which have a large dot product with one another, are going to be close in L2 norm. Okay, so there's this very simple relationship here showing that we can now just search for a column in my X matrix and a column in my Z matrix which are close in L2 norm. Okay, so we haven't really solved this problem of having the quadratic cost of searching across all pairs yet, but we've sort of slightly translated this problem into finding, we've got a point cloud here and a point cloud here, and we want to find the close pairs of points. Okay, so maybe I can just sort of comment. And this is, you might think that this is perhaps the origin of the name of the algorithm that I'm going to talk about. That's XYZ algorithm, because we've got this X matrix, we've got the response Y, and we form the matrix Z, and that's sort of almost true. But actually, what happened was we couldn't figure out a name for our algorithm, and at some point we had a placeholder for it, sort of XYZ, which we thought we'd then do a search and replace when we came with the proper name later on. And then I think I mainly blame Nikolai for looking at this and thinking, aha, maybe we can call it XYZ, because there's these matrices here. Okay, so we're looking for close pairs between these two matrices. Now, these matrices are sort of n by p. Okay, p the number of variables. Now, if the matrices were actually 1 by p, so the number of observations was 1, then finding the closest pairs of points between these two is a very easy problem, because I can just, rather than searching across all pairs, I just sort of put them on a line, sort them, and then you can easily just look along and find the close pairs that way. Okay, so that's obviously a bit of a silly situation, but what we can do is try to sort of project down each of these matrices x and z to a single vector of points, and then perform the sorting operation to find the close pair. So that's what we're going to do. So we're going to consider using a random vector, project down the x matrix and the z matrix to vectors here, and then we're essentially just going to sort them and hope that the distances between the projected points are reflective of the distances between the original columns of the x and z matrices. And of course, if we actually had an x matrix, a column of the x matrix and the column of the z matrix being so close that they were actually identical, then the projected points are still going to be identical. Okay. And so our strategy is going to be, let's use multiple random projections and collect together all the close pairs that we find using this approach, and then hopefully we'll retain the strong interactions that are present in the x and z with high probability. Okay. So what this gives us is this sort of this general version of the XYZ algorithm, and I call it the general version of the XYZ algorithm because there are lots of things that we still haven't decided yet. So we've got to decide what the distribution of this projection vector is. What sort of distribution should we take for that's going to make this search efficient? And how close is close when we sorted our vectors and got these close points? So this parameter tor here is the threshold under which we decide that things are close after sorting. Okay, so there's these two sort of important things that we've got to decide. L is the number of times that we're going to perform this, and that's perhaps less critical because you'd think, okay, we'll do as many of these random projections as we've got the sort of computational budget available. And gamma is just telling us, well, how strong an interaction are we interested in? So this would depend on the sort of practical application, and in the regression setting, we'll see that there's a sort of a concrete choice for this that we'll use. Okay, so just to recap, we've formed this matrix Z by multiplying the rows of the X matrix, and then what we're going to do is project each of these down using this random vector which has a distribution G, and then we find the close pairs from the projected points, do this L times, and then collect together all of the pairs that we found, all of these candidate interactions, and we check which ones of them were actually the sort of strong interactions. Okay. So we'd like to understand what would be a good choice for this distribution for the random projection vector, and also this how close is close, and this parameter tor. So what we're going to do is consider different subclasses of this very general version of the algorithm that I presented. So one sort of obvious choice perhaps is to take the elements of this random projection vector R to be IID with some fixed distribution F, so Gaussian, for example. Okay, so that's perhaps at least that was the first thing that we thought of, and perhaps it's a natural choice. And now and here, so in this sort of, I'm thinking of this as a subclass of all of the algorithms, where I'm leaving this parameter tor free, so we don't yet know how to pick that. Okay. Another class of algorithms we might want to consider involve some subsampling as well. So we might think that maybe this random projection vector, it might be helpful to have it a bit sparse. Maybe that helps us out. So this class of algorithms here is saying, well, let's sample m indices, where this m could be a random number, and just consider setting those corresponding entries of R to be non-zero, set everything else to 0, and the ones that we've selected from this subsample, we set them to be sort of IID with this distribution F. Okay. So that's obviously a very large class of algorithms, and this is a subclass of that, which is very much smaller, where what we're going to do is set this m, the subsample size, to just take 2 consecutive values, and the close pairs parameter we're actually going to set equal to 0. So we're asking, in this class here, for sort of exact collisions. We're asking for, we've got our X matrix, we've got our Z matrix, we're taking a subsample of the rows from each of them, and we're asking when do we find columns within this subsample which are exactly the same. Okay, and so the nice thing about this one is that the distribution F doesn't matter at all. It doesn't feature in this because we're asking just for these exact matches. This is obviously a very much smaller class of algorithms than this, and this dense projections, as I said, is perhaps the most natural one to think about. So we want to compare really the performance of algorithms within these different subclasses in order to decide what would be a sort of a good approach to take. So what I'm going to do is define this quantity here, which is just the number of times when we see agreement between the pointwise product between columns of X and the Y. I'll call this the interaction strength of the pair of columns J and K. And I'm going to let this J star K star correspond to a strongest interacting pair. And now in order to compare these subclasses of the algorithm that we've got, I'm going to think about restricting the algorithms to have a power at least some pre-specified value eta. Okay? And by power I mean it's the probability that we manage to catch this strongest interacting pair. Okay? So the other thing that I'd like my algorithm to be is I want it to be fast, so I'm going to let this T of the algorithm be the computational complexity of it. Okay, so we've now got these sort of these subclasses where we're restricting the power, which is telling us that our probability of detecting this strong interaction is at least something, and among those algorithms we really want to find essentially the fastest one. Okay, so what we're going to do is compare these different quantities here. The smallest computational complexity we can get inside this class, where the power is at least this parameter eta. Okay, so one relationship is sort of already obvious. We know that this minimal subsampling class is contained within the much larger subsampling class. So we know that the best computational complexity we can get from there has to be at least as big as this. We don't really know how big this gap would be. It's not obvious how large that gap would be. It's not obvious whether the dense one sort of wins overall or what happens there.
Can I just take F to be a mixture between something continuous and something that has a point mass at 0, and then just recast the subsample case as an example of the dense case? If I take F with probably 1/2,
yeah, so it's,
or say probably M over.
Yes, it's a good point. I mean, so we have this sort of slightly technical. I mean, I think that probably we could do that, but for the proof, we're not able to do that. I think because so here we're subsampling with replacement, so it's slightly different. So that would be. So I think ideally we'd want to do that, but somehow in the proof we couldn't get that to work. But yeah. In practice, I think that's what you would want to consider. Thanks. Good point. Okay, and so we initially thought that this sort of dense one might win, but what we ended up with was the following result. So here we're going to think about an asymptotic regime where we're potentially allowing sort of everything to depend on n. N's the number of observations, which is going to tend to infinity. So we've got these sort of relatively mild conditions here. We don't want there to be too many interaction strengths which are the same as the maximal interaction strength, because really what we're doing is asking the algorithm to find a particular interaction that has the strongest interaction strength, So if there are lots of them that have the same strength, it's going to be, it will take a very long time to find that particular one. For some technical reasons, we want this to be bounded away from 0 and 1, and we also don't want the interaction strengths to be sort of bunching up really close to the strongest one either. And that's what this condition here is saying, but it's really relatively mild. And so what we obtained is sort of was surprising to us, at least, is that so first of all, this minimal subsampling class, so the best computational complexity we can get from that is actually the same as in this much wider, much larger subsampling class. Okay. And then also, the best that we can get is actually subquadratic in the number of variables. Right? So we're beating the cost of a brute force. Now the dense sampling regime, actually this doesn't seem to help at all. So this performs really very badly. And what we found in practice, so we tried out the sort of IID Gaussian case to begin with. We realized it was really doing very, very poorly to our surprise, and then we're able to show that actually we know that it's going to do badly. So it's, we're not going to beat a brute force approach with Gaussian random projections here. So it's sort of quite. Is there a question, John?
Yeah. Sorry.
Yeah.
Can you define T of C again? It's the time to find the interaction with probability like a half or something?
T of psi?
Yeah.
Yeah, so it's just, I mean, psi is sort of determining everything about the algorithm that you would need in order to know what its computational complexity is. And I'm only considering the size, which is they're indexing the parameters of the algorithm, and I'm only considering those which have power at least.
Oh, eta is the power.
Yeah. Yeah.
Okay, thank you.
Yeah. So yeah.
No, it's the computational complexity.
So T is the computational complexity.
Eta is the power. T is the computational complexity.
Yeah.
Mm-hmm.
Okay.
Yeah.
Good.
Yeah.
Thank you. Sorry, I just lost notation.
Sure. Yeah. Yeah. Good. Okay. Any further questions at this stage? Okay. So then the nice thing about this actually is that because this minimal subsampling class is sort of winning amongst all of these, well, the nice thing is now we don't really need to pick this distribution G anymore. It doesn't matter what it doesn't matter what the distribution the distribution F is. Really, we're just asking for exact matches. The only thing that we have to pick now is this subsampling size M. So we've just got this one parameter left to choose in a way. Okay. So just to recap, so the form that the algorithm now takes is as follows. So we're really just so we form our X and Z, of course, and then what we're doing is picking some random indices, and then we can take our random projection vector to just have, let's say, IID uniform 0, 1 components, but we could pick anything there that we wanted to. And then we form our projected X and Z, and we just look for exact matches here. Okay, so we look for the points where points from our X vector actually lie exactly on the Z vector. And we retain those interactions, and then we can, for those candidate interactions, we can check, well, is the interaction strength actually as large as we wanted it to be to begin with. Okay. So now we can think about the computational complexity of this version of the XYZ algorithm, and we have this result here. So let's suppose this M, which is the subsample size, suppose this gamma 1 parameter is defined, which is a function of M, is p to the power of -1 over M. And let's suppose that the number of interactions which are stronger than this gamma 1 is sort of order p. So there are not too many of them. So you think about the sort of a histogram of interaction strengths that you might have. We're thinking that this gamma 1 is sort of on the right-hand side of it, so there's not really so much in the tail here. And suppose we're interested in finding interactions of strength at least gamma, and gamma is going to be sort of slightly further in the tail than that. Okay. And this number of projections that we're going to perform suppose that is such that the probability of finding an interaction of strength gamma is at least eta, then the overall computational cost of our algorithm takes this form here. So you've got the factor concerning the probability with which we're going to find this strong interaction. And then here, the main thing, the interesting thing here is this exponent in p, which is 1 plus log gamma over log gamma 1. Okay. So for example, if we're really interested in strong interactions with interaction strength greater than 0.9, and our gamma 1 was 0.7, somewhere around here, then here we have an exponent in p of 1.3, so really beating the full quadratic cost with this approach. So of course, if you really have a lot of interactions, so maybe, let's say, rather than this being unimodal, you have sort of an extra hump coming up here or something like that, then this result is really not going to be so helpful. You're going to incur a very large computational cost if you're interested in finding a particular interaction of strength gamma. But if there are lots of interactions which are very, very strong, then it's going to be hard to find one particular one of that strength, but you might be able to find sort of any interaction that is reasonably strong. Okay, but that's not the probability. That's not the task that we're asking of here. Okay, so this choice of m sort of relied on this gamma 1 being somewhere in the tail of this distribution. We can be slightly more precise about what m we want to pick. We can look at the computational complexity of the algorithm and try to minimize that with respect to m, and we see that we want to minimize a quantity of this sort of form. So in this objective function here, we see that we've got all of the interaction strengths inside here raised to the power of m. So this is not something that we know unless we really computed all these interaction strengths, but we could sample interactions and get some sort of idea of what this quantity here is, and then try to minimize an approximate version of this objective function. And that gives a reasonable choice of m that seems to work well in practice. Okay, so thus far we've really been thinking about this very simple setting, binary x, binary y, and we're trying to find these large dot products. So let's take sort of one step in the direction towards regression, try to increase the complexity. Let's consider the setting where our response is continuous. Okay. So if we write this dot product here in this way, it suggests perhaps a way of adapting our earlier algorithm to the situation of continuous y, because I can write this dot product as a dot product, or sort of a weighted dot product between a binary vector, which is the sign of y, and the pointwise product of the columns of x. Okay. So what this suggests is a weighted version of this XYZ algorithm, where we're weighting our sampling according to the absolute values of the entries in the response. And so so before we had this result to do with the complexity involving the interaction strength, which is the probability of getting sort of an exact match when we look at the y and we look at the pointwise product between the columns of x. And the corresponding quantity in this continuous setting here is this probability, which we can write now in terms of the original y this way. And you can see this is, of course, sort of, a function of the quantity that we're interested in, this dot product here. So our approach is going to be directed towards these large dot products in the way that we want it to be. Okay. So that sort of continuous response. If we have continuous predictors, what we essentially try to do is a transformation of the predictors that sort of makes them binary. And one approach is this sort of randomized unbiased transformation, where first we're just going to assume that all the entries in X are in -1, 1. If they're not, what we can do is divide the rows by the row-wise maxima to get them in -1, 1, and then multiply the corresponding entry of Y by the square of the row-wise maxima. And then the problem doesn't change at all, and we've got our X bounded as we need it. And then what we can do is create a sort of a randomized transformed version of the X, where we're going to set it to 1 with the probability X depending on the size of the entries in X, and -1 with 1 minus that probability. And if we look at this transformation, then again we're going to get that the interaction strength, the probability of there being an exact match, a collision, is again a function of this dot product that we're interested in. It turns out though that this doesn't work so well in practice, because if your data really has some outliers, then by squashing everything into -1, 1, you can squash a lot of the entries close to 0, and then this transformed version here is just going to be sort of 1 or -1, more or less with probability of half if these are then close to 0. And so what tends to work better in practice actually is this is a very simple approach. Just replace X by the sign of X, and so this is a binary version of this, and then just apply X, Y, Z onto this sort of transformed version of X with this deterministic transformation. And of course this XYZ algorithm is only going to suggest to us candidates which are strong interactions, and then we can go away and test them to see if the interaction strength is greater than the threshold that we're interested in. So that's sort of one approach for continuous predictors. But if your X is continuous, then you may well not be pointwise product type interactions that you're interested in, of course. So there are lots of different approaches that one could take in this setting. Okay. So that was still all just about dot products, and let's now move to the regression setting. Okay. So let's suppose that what we really wanted to do was apply the lasso to all our interactions. Okay, so this matrix W is going to be a matrix containing all of the pointwise products between pairs of columns of X. And suppose this is the optimization problem that we'd like to solve, and perhaps we might have a different penalty parameter for the interactions and the main effects, but that doesn't matter so much. But of course, what we'd like to do is avoid computing this matrix W involving all of the interactions and the quadratic cost in P that would come along with that. So let's just think about what would happen if we were to work with this P and where things break down if we were to apply sort of usual algorithms for the lasso. And among the fastest algorithms for computing the lasso is this sort of active set type approach. So we're interested here in computing the lasso on a grid of lambda values that are decreasing. And the way that this active set algorithm works is essentially you would have a guess of the support set of the beta, which is the main effects, and the support set of the theta hat, which are the interactions, and then you try to solve the lasso just on that active set, setting everything else to 0, and then you go and check, was your solution actually correct? Okay, and that's essentially what this is laying out here. So we compute the lasso solution just on these active sets A and B, and then you look at the KKT conditions to check whether you actually got the correct solution there. And if you have no violations of the KKT conditions, you know you've got your solution. If you have some violations, you add them to your active set and then recompute the lasso again. So really, the thing that hurts in this algorithm is this KKT condition check here, because you're always solving the lasso on a small active set, hopefully. But here you're really having to loop across every single column in W, so you're computing order p squared dot products between the columns of W and the response that you've got there. Okay, so that's this is the bit that is going to make is the computational bottleneck essentially. But you see that this KKT condition check that you've got is really of the form of the sort of dot product search that we were looking at earlier, right? So here you can think of this response here, think of this as the new Y, and we're looking for pairs of columns such that when we take the pointwise product, the dot product with the response exceeds this value of the tuning parameter, lambda. Okay, so what we can then do is essentially use our weighted the version of the XYZ algorithm with this weighted sampling to try to find the violations of this KKT condition with high probability. And you see that this interaction strength threshold that we had before, this gamma, can be chosen based on the tuning parameter here, based on the lambda. So essentially here you can, this sort of shows that really if you have a fast way of computing these dot products, you can sort of embed that into a lasso type algorithm to speed things up. And this is maybe one way of trying to compute dot products in a fast way. Okay, so I'll just try and finish now with a few experiments. So here we looked at a GWIRES data set with around 680,000 variables. And this here you see is the histogram of the interaction strengths that just on the actual data. And what we did was we ran this XYZ algorithm for a certain amount of time, and a sort of a competitor algorithm also based on random projections, which is a nice idea as well, called EPIC. And then we looked at just random sampling of the interactions. So ran all these algorithms for a certain amount of time, and then recorded what's the strongest interaction, the strength of the strongest interaction that we've found at that point in time. So this is here a run on the actual data, and you see as time goes on, we're not really getting very strong interactions, which is perhaps a little bit disappointing. Perhaps there are not strong interactions in this data itself, but so what we then did was try to embed and sort of artificially create a response where we have we've planted an interaction of strength 0.8 in this one and 0.95 in this other one here. See how quickly can we find it with the XYZ algorithm. And you see here the green curve corresponding to XYZ is finding this interaction pretty quickly. The other algorithms here seem to be slightly lagging behind. And here again we managed to find it reasonably quickly. Sort of brute force is not doing so well, but this EPIC is sort of slowly catching up, perhaps. Okay. And then here we're looking at the regression setting. So we looked at 3 real data sets. This is a gene expression one, a gene knockout, and some climate data simulation. And we looked at varying numbers of predictors from these data sets. So we subsampled varying numbers of predictors, and then considered applying the lasso to all interactions. So we looked at so P was relatively small, so that we could actually look at all interactions there, and compared to our approximate version with this XYZ. And you see that as we increase the number of variables, which then makes the algorithm take longer, we're sort of managing to get the same mean squared prediction error with XYZ as compared to GLMNet on all of the predictors with less computational time in a way. So it seems as if we're not losing out too much with this approximation. Okay, so there are a few more experiments you can see on the paper, which is on the archive. So I'll just sort of summarize that these sorts of maybe slightly more conventional approaches where you look at the main effects first, they could miss these strong interactions potentially. And this XYZ algorithm at least gives us a way of finding at least the strong interactions, and those are perhaps the ones that we'd really be interested in. So we might miss some weak interactions, but perhaps they would be of less interest to us anyway. And essentially, this XYZ algorithm, it's really a sort of an algorithm for finding large dot products in a fast approximate way. So if there are other sorts of problems which involve finding these large dot products, then it's perhaps something that can be embedded within that algorithm to speed things up. So there's a package on Tran as well, if you want to try it out, and thank you very much for listening.
So have you looked at approximate nearest neighbor method? So one reduction could be that for each column of Z, try to find the approximate nearest neighbor of X, and then do that for all the columns of Z. So if you can do that in sublinear time, then overall you would get subquadratic time.
Yes, I mean, I guess this is in a way an approximate nearest neighbors method.
How does this compare with existing?
Well, so that, I mean, there are some approximate, so I mean, this is an example of locality sensitive hashing, which I guess is, some people use as a pretty similar thing for these sorts of approximate nearest neighbors problems. But if you're, I mean, the other sorts of approach that people use is based on sort of the Johnson-Lindenstrass lemma in a way. And there you're more interested in, you're often interested in preserving pairwise distances between all of your points. Right, so that would be corresponding to this Gaussian random projection type approach. And the issue there is that although they manage to preserve all pairwise distances so that they're not too much error, we're really interested in preserving just the very closest distances. So that's perhaps slightly different. But so essentially any approximate nearest neighbors method can be sort of plugged into this, and
because one advantage would be, for instance, for continuous features, where you can use, so some of these approximate nearest neighbor methods will also work for continuous features. Just
right, okay.
Because so there, for instance, with locality sensitive hashing, it's actually also based on dense projections, but then it quantizes them and then does multiple of them and puts them together. So I guess that coupled with your theorem that I suppose without the quantization, just a dense projection is not good enough. So that's, you don't get subquadratic time.
Right,
so
yeah.
It would be interesting to extend your results to those kinds of the actual locality sensitive hashing, which I think is just multiple of these and then quantizing them and just putting them all together. So just something to
right, okay,
possibly
yeah.
So I guess what I missed was, what is the optimal choice for optimal scaling of M in terms of N and P? Because that would presumably determine the overall complexity of your problem, right?
Yeah, so that's, I just go back to this one. It's sort of depending on it's not just dependent on N and P, because it depends on really the whole sort of the histogram of these interaction strengths in a way.
You don't know that, right?
Which you don't know, yeah.
So what do you pick? Like, how do you pick it?
So we do some sampling here to sort of have an approximate version of this, and then we can minimize this quantity, and then this is what we use. But of course so you can't compute this thing exactly here, because that would mean that you did actually scan across all the interactions.
And so if you look, it probably goes back to Pradeep's question. There's a textbook example called the closest pair problem, right? That's usually solved by divide and conquer, and O of P dot P in your case, I guess. But there's a complexity of each iteration, right? And how does that compare?
I think those type of approaches, they can be, so they're good in terms of the number, they scale very badly in terms of the dimension. So they often don't care about the dimension and think of this as being fixed. And our dimension is n, essentially. Each of these points are n-dimensional. And they are typically they have a factor which is exponential in the size of the dimensions. You have sort of exponential in n and then something linear in p or p log p or something like this. So we weren't able to directly use those sorts of approaches.
Maybe do you have any specific applications in mind where you expect strong interaction effects without the main effects? Like what that motivated this?
Well, so I guess it's more to do with I mean, maybe lots of people have looked at data sets and they said, oh, there are no interactions here, but this is perhaps because they looked at the main effects first and then we're only able to look at interactions among these. So
an additional approach that you could do this
on
and then you could also
do this on top, yeah, to see if there are any sort of strong ones that could be missed. So I mean, it's not necessary that we really expect in all data sets there are lots of these sorts of interactions, but it's more that if we don't have a way of checking whether they're there or not, then we don't really know if they're there. So I guess I mean, there might be people in the audience who know much more about this, but there are examples in genomics where you sort of know that through twin studies and things like this, you know that the prediction error of your regression should be below something, but if you just do your main effects regression, you don't find this, and maybe if you include interactions between main effects, you don't find it. So you know that there are some interactions there, but you can't find them. So perhaps they're sort of hard to find interactions, or I guess they could be higher order interactions as well, perhaps. But, and then maybe something like this could at least try and find some of the pairwise ones if they're reasonably strong.
Thanks, and if there are no more questions, then let's thank all the speakers again. And,